is 1 over cosine theta. Tangent, we just said, I erased it a second ago, was sine theta over cosine theta. Good. Sine theta over cosine theta. And then plus cotangent was the other way around, right? Cosine theta over sine theta. Okay, all right. Well, at least I have it rewritten where all I see is sines and cosines. The next step is for me to clear the fractions. That means I'm going to multiply both sides of this equation by the LCD, the least common denominator. So what is the LCD for this problem? Do you all know? You need a sine theta. You also need a cosine theta. See, look at the denominators. And you need to multiply by something that contains everything you see down here. So this has a cosine, that has a cosine, so I'll need at least one cosine. That has a sine, so I'll need at least a sine. So I'm going to multiply the left side of this equation by sine theta, cosine theta. And then on the right-hand side of the equation, I'm going to multiply by sine theta, cosine theta. I'm clearing fractions. Oh, shit. I didn't even know we had one of those in here. Is that new? Has this been here this whole time? I don't remember ever seeing that. Understand what I'm doing here? Clearing fractions. Multiply this through. What do you get? Just sine theta, right? Because the cosines cancel. So you get just sine theta over here. Okay, be careful on this multiplication through. You've got to do a distribution. It's got to go here, and it's got to go here. So on that first multiplication here to here, what goes away? When you bring this in here, what cancels? The cosine, right? How many factors of sine will you have? 2 factors. So this will just be on this first multiplication, just turns into what? Sine squared? Do I need to show that, or are you all comfortable with that? Y'all okay? Yes. Plus, now when I go from here to here, what do I get? Cosine squared theta? Ooh. Sticker to somebody who can, I'll give you a little happy little smiley sticker if someone can tell me what the right side of that equation is. 1. Why is it 1? This right here, this super important identity that you're all going to get tattooed on your backs this weekend, right? One of my favorite tattoos I've ever seen before is this guy who has this unit circle on his back. It's really awesome. Yes? Did you have a question? Oh.
How would you even see that?
Pardon?
You would just like look over like during a test? Or
No, just get it to have it. Just pretty badass, right?
like what would you get it?
What, the unit circle?
Yeah.
Why would you get the unit circle?
Like just for fun? Like just to get it? Just for shits and giggles?
I don't know. Yes?
Can you explain to me how you multiply the sine and cosine?
Okay, so you want to see one of these come through?
Yeah.
Okay, so I have sine, let me do it this way. I have sine theta over cosine theta. That's this, right? I'm going to multiply this to it. So when I multiply it, I hit it with the sine theta, cosine theta. You have to remember that this right here is really like over 1, right? So when you multiply here, anything that's common can cancel. And so I have 2 factors of sine still that multiply together to become my sine squared. Yes? All right, what was the other question? Same thing? Do I need to show the other one? Or are you okay? Yeah? I don't mind writing it. I don't think, I mean, the tattoo's not a bad thing. What's going on?
Can we get extra credit?
Depends on what it is, I guess. That's the second multiplication through. I have one tattoo on my body, and it's mathematical.
What is it?
It's a,
You're a math teacher.
it's,
I understand.
well, this guy likes math too, I guess. He has a unit circle. I guess he likes it. Mine is this, that right there. So it's simple. It's just, yeah, it's a cool looking symbol to me first, but this is what we call the line integral. So it's a way of, imagine you have like a, I don't know, well, it has to be a closed. Imagine you have a particle moving through space, three-dimensional space, through some sort of like electric field, like a vector, we call it a vector field. Then this would basically add up. You get what's called like the total charge on the whole path. Yeah, it's a cool symbol, and you have to go pretty far into the math to understand what that is, and I liked it. To me, it was better than, you know, barbed wire or something. Not if you have barbed wire, no offense, but I'm just saying, like, to me, like that, you know, some people get tattoos and 10 years later they're like, shit, you know, why did I get that, huh?
Where do you have it?
I can't show it. It's on my back. It's on my back. It's on my back. Yeah. But it was planned. Like, I knew when I finished grad school, I was like, first thing I'm gonna do is get that tattoo. So I didn't say it wasn't a drunk tattoo. It was a drunk tattoo, but I knew going in. Like, it was planned. Yeah. All right, so sorry, the right side is 1. Sine theta is 1, right? And now what is this saying? Where on the unit circle is the y coordinate 1, right? So that's up here. So that's just pi over 2 plus 2 pi k. There was 2 other things I wanted to get tattoos of. My number 1 option was too much detail in it, and then, you know, by the time I'm like 70, it would just look a big blob on my back, you know. So I was like, no, I won't do that. But there's another one that's very famous. It's this one. I don't know if anyone has ever seen this before. Has anyone ever seen that equation before? No, probably not. This is argued to be the most beautiful equation in math. I mean, it's subjective. A lot of people think that this is the most beautiful equation.
The spiral one?
Are you thinking of the Fibonacci sequence, the golden ratio, golden spiral? That's not this. Yeah. So this is argued to be the most beautiful equation in math because it brings together all of the most important numbers in math. 1, which I know we all sit here and think that 1 is like dumb. 1 is that 1 is important. But 1, in our number system, 1 is called the multiplicative identity. And all fields must have a multiplicative identity. So 1 is our multiplicative identity. 0 is the additive identity. Pi, you all know, has something to do with a circle. E is that exponential function that's very special. You'll learn in Cal 1 why it's so special. And then, of course, I is the imaginary number, which a lot of you have been told is imaginary. And I told you all about how you need 4-dimensional space to actually get it, right? Remember me telling? So even though I has a bad rap, this is actually a very important number. And so that equation brings them all together. So some people get that tattooed. I thought it would be too cheesy to get that because a lot of people have that already. All right, why are we talking about tattoos? Unit circle. Go get the unit circle tattooed on your back. No extra credit. All right, I think that I have exhausted us, right? So back on the homework, page 647. I would like for you to now look at problem 61 through, let's just go to 83. Odds. And do what you can, right? Every problem in that set is somehow similar to something I did here. I do need to point one thing out that might come up in those problems. Do you remember when I did this earlier and I said, hey, anytime you see cosine theta, that it's the same as cosine negative theta, right? Because they're even. There's a problem in there where it has sine of negative theta, and that is not the same. So for sine, it works like this. Negative sine of theta equals sine of negative theta. So if you have a negative inside the sine function, a negative theta, what you can do is you can turn it into a positive, but you have to put negative on the outside. So like if you had a problem that looked like this, let's just say, I'm totally making up this problem. Let's say you were trying to set that equal to 0. Try to solve this, right? This has negative theta, that has theta. What you could do is replace this with minus sine theta equals 0. Okay, you could do that. Notice though, I'm not just getting rid of it. I have to change the sign out here. With cosine, you can just get rid of it, make it positive, and nothing else changes. With sine, you have to change this to a negative out front. Okay. Let's plan for a quiz. Yes?
And do you break down
The 2 sine? Yes. Yeah, if I were continuing to solve, yeah. I just was showing you what happened here, but yeah, this would continue here. Yeah, and then dot, 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 whatever happens. Don't go trying to solve this. I just made this problem up. Yeah. Let's plan on Tuesday to have a quiz. So I'm going to give you a quiz over, let's make it a nice quiz. I'll be friendly. I'm going to make it over one problem from that set. All right? So here, I'm going to pick one problem out of here, and that's going to be your quiz problem. So do the homework, review the homework, and be ready to do exactly one of those problems. Oh, you want to use the homework as well? Yeah, let's try that without it. I've told you exactly, I've given you a set of problems that your quiz is going to come out of. So if you do them all, understand them, you should be okay. All right, we still have some time. I know you want to go, but we need to at least start talking about the next section. Historically, this is one of the least favorite sections for most students. I'm just being honest with you, okay? I don't want you to... So this section, 8.4, is called trigonometric, I'll just say trig identities. Trig identities. What makes this section really difficult is that there are all these relationships that we have between sine, cosine, tangent, cotangent, secant, cosecant. They're all like have this very weird connection to one another. So what we're going to do here in this section is I'm going to give you a statement that's true, and then you have to show that it's true. You have to prove what's called an identity. So I'm going to give you an example to start, just so you can see like a first example. Which one do I want to do here to start? Yes?
I'm sorry, but...
Don't apologize.
Do we give it to you after class?
What, the one that I wanted for today?
Yes.
If you have it, I will collect it as an extra credit. Okay? If you don't have it, you don't have it. It's not going to hurt you. But I would recommend that if you're going to turn it in, to maybe like take a few pictures of it like before you turn it in, and that way you have access to your own work if you're trying to do your homework and need it for some reason. All right, let's start out with something Very straightforward and simple, all right? Show that cosecant theta times cosine theta equals cotangent theta. So look at the instructions here. I want you to show me that that statement is true. Am I asking you to solve an equation? No. I'm not saying go solve for theta like we did in the previous problem, right? It's not what I'm asking you here to do here. I'm saying that this is true, that this side of the equation equals that side of the equation. I want you to show it, prove it. So the way you do this, and the way all of you have to do this on a test, is you are going to start with one side of this equation. You're going to write it down, and you're going to do a bunch of manipulations until it turns into the other side of the equation. So you're going to start with the left-hand side and try and turn it into the right-hand side, or you're going to start with the right-hand side and turn it into the left-hand side. You cannot, though, treat this as an equation right now. So let me just work through this one. So what I'm going to do first is this. I'm going to write down, I like to do this, LHS, left-hand side. Okay? The left-hand side of that equation is cosecant theta cosine theta. That's all I'm going to write down. Okay? That's the left-hand side of the equation. What I need to do is somehow manipulate that and convince you that that's equal to cotangent theta. All right? So here's what I know. This, let me erase this. I need to somehow get to the right-hand side of the equation. The right-hand side over here was cotangent theta, right? So somehow I've got to get from there to here. Well, what do you know here? Cosecant theta is what, by definition? 1 over sine, right? So this is 1 over sine theta times cosine theta, right? But that can be pushed on top, can it? So this is really just cosine theta over sine theta. But what is that by definition? Cotangent theta. And therefore, I've gotten to the right-hand side, right? I started with the left-hand side. I did some manipulations, and I have convinced you, hopefully, that it is indeed the right-hand side of the equation. What I never did, though, was wrote down the original equation and started like multiplying both sides by something. No, I didn't do that. I started with the left, turned it into the right. Let's do another one. Show that sine theta times, in parentheses, cotangent theta plus tangent theta, let me just double check that. Yeah, equals secant theta. Show that that's true. Prove to me that this big ugly statement over here is really just secant theta. So you're going to start with one side and turn it into the other. Generally speaking, the side you start with is the one that looks more complicated. Which in this case is which side? Which side of that equation looks worse to you? The left side. That's where you usually start, with the one that looks worse. So I'm going to start over here, I'm going to write left-hand side, and what I'm going to try and do is turn it into the right-hand side. So here we go. Sine theta, and then cotangent theta plus tangent theta. That's it. That's all I write. Right? That's the left side. Now that I can do what with? What can I do? Whatever you want. I mean, look, as long as it's legal, you can do it. Yes? What's that? Turn cotangent into cosine. What over what? What is this? Cosine over sine. Turn this one into Okay, so I'll write that down. I agree that this is equal to sine theta, parenthesis, cosine theta over sine theta, plus then sine theta over cosine theta. Any questions? That's just me rewriting what cotangent and tangent are. Any ideas what you want to maybe do next? I don't know if, I think you were meaning like this. This is not an equal sign, so we can't do anything like that. I heard something else. Distribute? Multiply the sign through? Can we do that? I'm okay. As long as it's legal, I'll do it, okay? Distributing a sign through is fair? Here? Yeah? Let's try it. Shit. I mean, what do we have to lose, right? So what happens when I do this first multiplication? This sign onto this one, what happens? The signs cancel. And you're left with what? Cosine theta? Cosine theta. Okay, plus. Now, when you multiply the sine theta to the second one, does anything cancel? No. So how many sines do you have on top? So you have sine squared on top, theta, over the cosine theta that's still on the bottom, right? Okay. Yes?
Isn't cosine theta over 1? And you can cancel cosine.
This is cosine theta over 1. I agree with that. But you can't cancel these because that's not multiplication. That's addition. Common denominator? Or could we put these together in a common denominator? Could we? Does it make sense for us to try to? Think about what our answer is. Where are we trying to get to? We're trying to get to 1 over cosine, right? 1 over cosine theta. That's what we're trying to get to, right? So it makes sense to maybe put these together because then you would have cosine on the bottom, wouldn't you? Yes? Could you use the identity for sine squared? We could try it. Do you want to go down that road? Look, this is the thing that really drives people crazy about these problems. You're basically trying to get from point A to point B, okay? You're trying to get from the left-hand side to the right-hand side. As long as you're doing correct algebra, you're on a path, okay? Now, your path might look like that. Another student's path might look like that. My path might look like that. And some other student's path might look like this, right? Because the algebra can be anything you can think of. I've got students that want to get a common denominator here. I've got students who want to turn that into 1 minus cosine squared theta. Those are all legitimate algebraic steps. So you just have to choose a path and go. And you might wind up in just like, forget it, I'm starting over. That might happen. It probably will. All right? I hate grading these, by the way, because students will go on these paths, these journeys, you know? And there's really no way to teach you to get better at it other than just practice, practice, practice. And I can even tell you that the way I do it might be less efficient than a way that a student might do it. Like, I don't know. But you need to be confident that you can get there. All right, so what do y'all want to do? Do y'all like the idea of getting a common denominator between these two? Or do you want to turn that into 1 minus cosine squared? So we have differing opinions here.
If it's a common denominator, then it'll be cosine squared. It'll be cosine squared plus sine squared over cosine. Cosine squared plus sine squared is equal to 1. 1 is equal to cosine, or 1 over cosine.
Yeah, so part of what might make this easier is how far ahead you can see. How far ahead can you see? If I put these two together, I would need to multiply the top and bottom of this by what? Cosine. That would turn the top into cosine squared. And I'm going to add that to sine. That's a 1. Cosine squared plus a sine squared will be a 1 on the top, right? And then when they come together, they'll have the same denominator of cosine. If you can see that far ahead, then that's definitely the way to go. Now, that's not to say that the other way wouldn't work as well. Because the other way, if I look at the other way, cosine theta, that's a terrible marker. It's the closest I've been all semester. All right, if I do that, that's just this one, right? I think you can't do anything here because there's a subtraction. I think we'd still have to get a common denominator here. I don't see anything clean this way. I mean, I guarantee it'll work, but it's probably going to be more work. So let's go, we might look at that again. Let's just go with the common denominator though. So I'm going to multiply top and bottom here by cosine theta. Now if you like puzzles, you know, like little things that challenge you, these problems could be fun because they are challenging. So I multiply top and bottom by cosine theta. I get cosine squared theta over cosine theta plus sine squared theta. I'm taking my time here to show my steps here. So that's just me getting the common denominator, multiplying top and bottom of this one by cosine theta. Now I put it together into one big fraction, cosine squared theta plus sine squared theta, all over cosine theta. But that's just 1 over cosine theta, because the Pythagorean identity. But that's secant theta, and that's the right-hand side. Did you like that one or no? Questions? Do we want to see it the other way? No. No? No? You sure?
No.
I know y'all want to go. I'm going to at least put one more up here and just see how far we can go with it in 3 minutes. Y'all know what your homework is, right? I'm not going to assign anything from this section yet. So everything you're going to do is just what I gave you a second ago. All right, the last one we're going to just at least look at. Sine of u. We're going to use u instead of x. There's nothing wrong with that. Cosecant u minus, oh, this one's not hard. Cosine squared u equals sine squared u. Sine u times cosecant u minus cosine squared u equals sine squared u. Doesn't look good, does it? Start with the left-hand side. How can we rewrite this? Sine u times, yeah, this is sine u times 1 over sine u, right? That's what cosecant is. So the left-hand side is sine u times 1 over sine u minus cosine squared u. Right? That's my left-hand side. And what's that? That's a 1, right? I mean, basically that's over 1, and then these cancel. So this is really just 1 minus cosine squared u, which is sine squared u. So this formula works for any you could have thetas in here, x's in here, u's in here, doesn't matter. So 1 minus cosine squared u would be sine squared u. And that's the right-hand side. That one wasn't as bad, was it? Any questions on that one? All right, we'll do plenty more of these next time. There are, in the homework set for that section, there are the problems I'll ask of you. There are 92 problems in that homework set of proving identities, like showing, verifying identities. And so we just looked at like the first, I stopped, that's example, or that's number 28. So a lot to do still there. All right, everyone, have a good weekend, all right? Do your homework. Quiz on Tuesday over one problem from that homework set. Oh, if you want that extra credit or bonus or whatever, you can turn in your homework from last time, or the homework. Just put it right here on the corner and I'll pick them up. Where's that stack of paper? Did it get around to everyone? Are there any others?